Hi, in this video we are going to talk about prime numbers. This is the second video for the number theory section. So let's get into the discussion. So the first thing is, what is a prime number? So the way we define it is as follows. An integer n always has two different at least two different positive divisors, and these two positive divisors are basically 1 and n itself. Now, if the integer has no other proper factor, has no other divisor excluding 1 and n, then that integer n is a prime number. The integer n is a prime number. So basically, there are three kinds of positive integers. One is a special positive integer. Then there are two other kinds, which are prime numbers and composite numbers. So composite numbers have divisors other than 1 and n itself. They have some more divisors. Whereas prime numbers only have two possible divisors, which are 1 and the number itself. Right? So let's look at some of the properties of prime factor. The first property is an integer greater than 1. An integer greater than 1 must have a prime factor. Must have a prime factor. Now, this actually gives us a good number theoretic criteria to prove that an integer is equal to 1. So sometimes in questions you have to prove that something is equal to 1. So what we can say is we can establish it by contradiction, by assuming that the number under consideration has a prime factor. We can assume that the number under consideration has a prime factor, and using properties of prime factors or prime numbers, we can try and establish a contradiction, because if it has a prime factor, it is guaranteed to be greater than 1. So if there is a contradiction, then our assumption is wrong. The number doesn't have prime factors. And if it doesn't have prime factors, it must be equal to 1, right? So that is the idea. The second property is this one. Let P be a prime number, and N be any integer, So we have two choices. Then either P divides N exactly, or P is co-prime with N. So if you have a prime number and a natural number, you either have P divides N or you have GCD of P or N equal to 1. These are the only two options we have, right? So if GCD of P and N is equal to 1, then that is P and N are relatively prime or co-prime with each other. And other cases when P divides N, right? Now the third property of prime numbers is this one. If P is a prime and A and B are integers, then if P divides AB, that implies that either one of A or B is divisible by P. So P divides AB means either P divides A or P divides B. Okay, this is pretty obvious. The fourth property is that there are infinitely many prime numbers. There are infinitely many prime numbers. The proof is a very old proof by Euclid, and we look at the proof for this property. So we will do the proof of this by contradiction. We will say, suppose there are only finite number of primes. Suppose there are a finite number of primes. And let's say the list of primes is this. And those are P1, P2 till Pk. This is the finite list of primes. Okay. We have assumed that there is a finite number of primes and these are the list of primes. So P1 must be 2 and this must be 3 and so on. Right? Consider the number n, which is equal to the product of these primes plus 1. Right? So we know obviously that n is greater than 1. Therefore, n must have a prime factor. N must have a prime factor since it is greater than 1. And if it has a prime factor, then if P is a prime factor of n, then P must lie in the list of primes, which is P1, P2 till Pk. P must lie in that list of primes, right? So then if you think about it, let's write it like this: n minus P1, P2 till Pk equal to 1. If you think about the LHS, we know that P divides n because P is a prime factor of n. And we know P divides P1, P2 till Pk because P must lie in the list P1, P2 till Pk. So what we are getting from here is that LHS is such that P divides LHS, right? If P divides LHS, that implies that P divides 1. But that is a contradiction because there is no prime which divides 1, right? So that means our initial assumption that there is a finite number of primes must be wrong, because using that assumption we have arrived at a contradiction. We have arrived at the situation that the prime number P divides 1. That is not possible. Hence, there are infinite number of primes. Okay, the next property is the unique factorization theorem. Unique factorization theorem. And this property says that every integer greater than 1 can be decomposed into a product of prime numbers, product of a finite number of prime numbers. So any integer n can be written as product of prime numbers p1, p2 till let's say pk, and each prime number is appearing some number of times. So alpha 1, alpha 2, alpha k just tell us the number of times that prime number appears in the prime factorization of the integer n. Now, if you ignore the order of the prime numbers here, if you ignore the order of the prime factors in the product, basically whether 2 should be put first or 3 should be put second and so on. If you ignore the order, then the factorization is unique. This factorization is unique, which means that there are no two integers, or which means that a single integer cannot have two different prime factorizations. You always have one prime factorization for a single integer, and this is known as the standard factorization of n. So that's pretty important. Now, using this prime factorization, we can figure out certain other things. For example, what is the necessary condition for a positive integer d, for a positive integer d to be a divisor of n, divisor of n. So in order for d to be a divisor of n, we must have d should have the same prime factorization, but the powers could be different. D's prime factorization can also be written like this. But in this case, 0 is less than beta I is less than equal to alpha I, for I goes from 1 to k. So the difference is D should have the exact same prime factorization. It cannot have any extra prime number, otherwise it will not be able to divide n, right? In order for D to be a divisor, it should have the same prime factors, and the powers of the prime factors in the product for D should be less than or equal to the powers that are there in the original number n. Only then you can be a proper divisor, right? Power should be less than or equal to the source number's power. Okay, so that is also a pretty obvious property. Let's look at another one. Let tau of n denote the number of positive divisors of n. Positive divisors of n. And we have n is given by p1 alpha 1, pk alpha k. This is the standard factorization of n. So what is tau of n? Tau of n is the total number of positive divisors of n. So the total number of positive divisors is simple. You multiply the, the product of alpha 1 plus 1, alpha 2 plus 1 and so on till alpha k plus 1. Why? Because when you are constructing a new divisor, you have a choice whether to put what power for P1, right? So when I'm constructing a new divisor, I have these same prime numbers and I can choose whether P1's power can be 0 or 1 or 2 till alpha 1, right? So I have exactly alpha 1 plus 1 choices to select what is the power of P1. Similarly, I have alpha 2 plus 1 choices to select what is the power of P2 and so on, right? So the total number of choices by the multiplication principle, in order to select a divisor, you need to have this many choices. So these many positive divisors are possible. Alpha 1 plus 1, product with alpha 2 plus 1, and so on, right? Now, the next thing is basically find the sum of all of these divisors. Sigma n is the sum of the positive divisors of n. Positive divisors of n. Now, sigma n also has its own formula. The sigma n formula is basically this. Sigma n is equal to P1 alpha 1 plus 1 minus 1 by P1 minus 1 multiplied by P2 alpha 2 plus 1 minus 1 by P2 minus 1 and so on till Pk alpha k plus 1 minus 1 by Pk minus 1. So sigma n is also a product and it is basically adding up all the powers possible in all the divisors and adding up the numbers that are correspondingly formed. So this is the formula. You can show this pretty easily. When you try to add it, you'll get a geometric series in powers. So it is pretty obvious to prove, so I'll not do it right now. Let's move on to the next statement, the next property for primes. So the next one is this one. A positive integer n is a perfect square if and only if tau of n is an odd number. What was tau of n? Tau of n was the number of positive divisors for n. Number of positive divisors. And this was given by alpha 1 plus 1, alpha 2 plus 1, and so on till alpha k plus 1 if n's prime factorization was simply p1 power alpha 1 till pk power alpha k. So think about it. If n is a perfect square, all of the powers here, all the powers alpha 1, alpha 2 till alpha k must be even. They could be 0, they could be 2, 4 and so on, right? These are the possible powers if n is a perfect square. And if they are even, then alpha 1 plus 1, alpha 2 plus 1, alpha k plus 1, all of them are odd. Which means the product of the integers is also odd, which means Tn is odd, right? So that is the proof of the statement. It's pretty simple. The next idea is about LCM and HCF. So if you have A is equal to P1 power alpha 1, P2 power alpha 2, and so on till Pk power alpha k, and B is equal to P1 power beta 1, P2 power beta 2, and so on till pk power beta k. These are two integers with their standard factorizations. Then the GCD of A and B is basically P1 power A1 till pk power ak, and GCD of an LCM of A and B is P1 power B1 till pk power bk, where AI is the minimum of alpha I and beta I, and bi is the maximum of alpha I and beta I for all I goes from 1 to k. AI and bi are the minimum and maximum values of these two prime factorizations exponents, and after that you're constructing the LCM and the GCD in this way, right? Okay. The next property talks about a criteria for checking whether a number is prime number or not. So if n is greater than 1 and n is not divisible, n is not divisible by prime numbers less than or equal to root n, then n is a prime number. N is a prime number. So in order to find out whether n is a prime number, we will need to check all the prime numbers up to root n. And if there are no prime numbers up to root n that divide n, then n is also a prime number. So that is the meaning of this. So for example, if I want to check till 1000, all the possible prime numbers till 1000, right? So, or actually, I just need to check whether say 1001 is a prime or not, right? In order to check that, you need to check all the primes up to root 1001, right? So root 1001 is what? So 30 square and is 900, and 31 square will be something less than 1001. So yeah, it will be 961. So it is 31 point something, right? So what we will do is we have to check all the primes up to 31, all primes up to 31. And if 1001 is not divisible by any prime up to 31, then we say that it is itself a prime, right? So the number is a prime number if it is not divisible by prime numbers less than equal to root n. That is the criteria here. Okay. The next thing that we'll discuss is this notation. So for any integer n, for any integer m and prime p, the notation p power alpha and double arrow here m represents represents that P power alpha divides M and P power alpha plus 1 does not divide M. So basically, P power alpha is the highest power of P, appearing in the standard factorization of M. Appearing in the standard factorization of M. So for any n greater than 1, how do we find the prime factorization or the number of what is the exponent of a particular prime number in that integer, right? So we want to find alpha p, which is the exponent of prime p in the factorization of n. So the way we do it is alpha p is equal to summation L goes from 1 to infinity GIF of n by p power L. So what does this mean? This means for L is equal to 1, it is GIF of n by p, then it is GIF of n by p square, and so on till n by p cube, and so on. Eventually this series will terminate, and therefore you will have the highest power alpha p, highest power of prime number p that appears in n, right? So that is your alpha p. Now there is a alternative version of this formula. If you want to find the coefficient of the highest power here of prime p, we can also do this. Let the PRE representation of n be n is equal to ak minus 1 a0 p. What do we mean by PRE representation? So usually we use base 10 as our system of numbers. However, you can write numbers in the form of binary or ternary numbers. Ternary, where base is 3 and here the base is 2. So when I say PRE representation, the base is P and P is a prime number. So let's say the PRE representation of n will be this. We are writing the same number n but with respect to base P, right? So in that case, it can be expanded like this. N is equal to A0 plus A1P and so on till AK minus 1, P power K minus 1 plus AK into P power K. This is my N here. Now, what we want to find out is what is the power of prime number P in the expansion of N, right? So here we have in this series we have 0 is less than AI is less than P for I goes from 1 to K. Let S of P of N be equal to A0 plus A1 plus AK, right? So this is the sum of the coefficients or sum of the numbers that appear in the PRE representation of N. Now we can show or we can prove that alpha p is equal to n minus s of p of n by p minus 1. Let's work out an example and see how this works, right? So let's say our number n is 28, right? So 28 is basically 1 into 2 square into 7 power 1, right? And I want the power of 7 that appears in 28, right? I need alpha 7. That is what I want. I already know the answer is 1, but what we'll do now is try to do it in a different way. So 28 first I will write in a PRE representation, right? So I will use the base 7 because I need alpha p, where alpha is the power of the prime p, right? So base 7 28, if I try to calculate, so this is basically 3 into 7 power 1 plus 1 into 7 power 0. So it is equivalent to 3 1 base 7, right? 3 into 7 power 1 plus 1 into 7 power 0. No, that is incorrect, I think. 1 into 7 power 0 will be 1 only. So that is not correct. 0 into 7 power 0 and 4 into 7 power 1. That is the primary, that is the base 7 array representation of 28. It is 4 0, right? In base 7. Correct. So therefore, S of P of 28, which is the same as S of 7 of 28, is simply the sum of the digits here, so 4. And if you do the formula now, sigma P is equal to N, which is 28 minus S of P 4 by 7 minus 1, right? So that is coming out to be sigma P is equal to 24 by 6, so which is 4, right? Right. And if I have to do a find the powers of 2 that appears, if I want to find the power of 2 that appears, what should I do? I'm getting sigma p is 4, and sigma p I would have calculated by the normal method, which would be 28 by 7 plus 28 by 7 square. This would be 4 plus 0 and so on, right? So alpha p would also have been 4. So we are getting the same value of alpha p in both the methods, but the problem is that it doesn't seem like it is matching the powers of p, right? Okay, I'll think about this part. Perhaps there is some mistake in the derivation here. I'll let you know about this. For now, the theory that we needed for this section is done, and we look at a few problems that should help you apply the principles that we have learned in different settings. So question 1 is this one. Let m be a positive number, positive integer, and 2 power m plus 1 be a prime. Prove that m is a power of 2. Okay, so we need to show that m is a power of 2. So what we can try and do is we can show that if m is not a power of 2, we can show that if m is not a power of 2, that implies that 2 power m plus 1 is not a prime, right? So one common technique of proving that a number greater than 1 is not a prime, we have to show here that this is not a prime. So one common technique would be to show a prime factor for that number, right? So Since m is not a power of 2, that means that m, it has odd factors, right? It has odd factors greater than 1. Greater than 1. So we can say m is equal to k and r, where k is greater than equal to 1, r is greater than 1, and 2 does not divide r, right? Basically, m is not a power of 2, so it must be an odd number, right? And therefore has some odd factors. So what you can do now is we can write 2 power m plus 1 as 2 power kr plus 1, which is written as 2 power k power r plus 1 power r, which proves that 2 power k plus 1 is a factor of 2 power m plus 1, right? So we are guaranteed that if m is not a power of 2, it will have some odd factors. For example, 2 power k plus 1 is one such factor, which is a factor of 2 power m plus 1 in that case, right? Because m is odd, we can write it as kr, where k and r are odd. So because of this, that will prove that 2 power m plus 1 is not a prime, which is a contradiction to our initial statement where we said that it must be a prime. So we have gotten our contradiction, and therefore our initial assumption is wrong. And the assumption was that m is not a power of 2. That assumption is wrong, right? Okay. Now, the next question is this one. Let a and b be co-prime integers. A and b be co-prime integers. Prove that GCD of a square plus b square with ab is equal to 1. So the way we'll prove it is again by contradiction. We'll say let D be the GCD of a square plus b square and ab. If D is greater than 1, then D has a prime factor p. If the divisor or the GCD of a square plus b square comma ab is greater than 1, then D has a prime factor p, obviously. Any number greater than 1 has a prime factor. So then we know from D divides a square plus D divides AB, it implies that P divides AB, right? But P is a prime, P is a prime. So therefore, that implies that P divides A or P divides B, right? We are getting either P divides A or P divides B. Let's assume that P divides A. If we suppose that P divides A, then then we already know that P divides A square plus B square and P divides A. So that combines, we know that P divides B square, which means P divides B, right? And if P divides B, therefore P is a common divisor of A and B. Correct. That means that the GCD of A and B has to be greater than or equal to P, right? The greatest common divisor has to be greater than or equal to P. So we have already gotten P is a common divisor of A and B. But it was given in the problem that A and B are co-prime integers. A and B are co-prime integers, or GCD of A and B was 1. So we have P is less than equal to 1, which is a contradiction now, right? So we have established a contradiction. We have shown that the GCD of A and B must be equal to basically 1. Otherwise, you're getting a contradiction here. D greater than 1 is the wrong thing because we are getting a contradiction out of it. So D must be equal to 1, right? Okay. The next problem that I want to discuss is this one. Let P be a prime. Let P be a prime. Prove that P divides PCK for all k from 1 to till P minus 1. Now, this is a combinatorial coefficient. What we can use is some combinatorial analysis from the previous section. We know this identity PCK times K is equal to P times P minus 1 CK minus 1, right? This is an identity that we had established in the previous section. So from here, this means that clearly P divides K times PCK, right? But it has been given that 1 is less than equal to K is less than equal to P minus 1. So from here, we know that P does not divide K because K is smaller than P, right? Smaller than or equal to P minus 1. So P does not divide K and P is prime. P is prime, P does not divide K and P divides the whole thing, which proves that P must divide PCK, right? So here we are just using this combinatorial identity from the previous section and we are getting the proof. There are several other problems in this chapter that I want to share with you. So those will be part of the assignment for this section. So you should try them out yourself and we will be looking at the solutions of those assignments in a future discussion. So for now, that's it for prime numbers. We'll continue with the next topic in the next video. So I'll see you next time.